And on to some machining with my practically a toy Proxxon FF230 little milling machine. What I'd like to do here is make some hold down clamps for this vise that I got. I have some other vices. I got two of these little guys. They're made in India. And they got these slots for holding down. You can put some screws in there, and they line up nicely with the T-slots on the table. Now that's going to allow two different locations for mounting this vise onto the table. This location here may be for larger work pieces, that location for smaller work pieces. It's nice to have that little bit of flexibility, because a little bit of a quirk with this machine is that the table becomes a little bit more wobbly as you pull the table out. It develops a little bit of a slack in it, so it's nice to try to keep the table as relatively drawn in as possible. Yeah, these are not too bad vices. However, I don't really like them. I indicated off of them, and they do seem to be parallel with the table, and they seem to be okay. They're competent. And nonetheless, what I don't like about them is, well, they're a little bit on the rough side, for one thing. You pull the mobile jaw inwards, and it starts to bind a little bit. Also, the mobile jaw, it really does have a little bit of a wobble to it. It's just a little bit disconcerting. Now, in contrast, this new vise, which is not from India, but it's from China, I think it's the QGG series, these are made really, really well. There's practically no noticeable play in that mobile jaw. Acme threads instead of fine threads makes the opening and closing a lot quicker. Yeah, these are really nice. However, there's no simple way to mount this onto the milling table. What you could potentially do is use these step clamps, and you can use those, but they're a little bit finicky to set up. I find their clamping force isn't that great. So what I like to do is make some dedicated hold downs. Now I broke out Fusion 360, and well, I went to thousandth of an inch, and then I went to millimeters and hundredths of a milli. I went all the way to angstroms, and that wasn't good enough for my purposes here. So I'm going to break out RFT CAD, and I need it to be about thereabouts. About a finger width. Well, maybe not. I can do a little bit better than that. Let's get out a ruler here, and I need these hold downs to be, I would say, approximately 14. Yeah, it looks like about 14 millimeters high. Here's my stock. This here is 1¼ inch square bar of 416 stainless steel. 416, that is a free machining variety of stainless steel. I thought I'd give this a shot. This stainless steel is bloody expensive, or at least it is for a small hobbyist such as myself. I had to buy this on the internet, and I'm not going to say how much I paid for it. Whatever the case, I got to be really careful with it. I got to waste not, want not. I have a Sharpie mark here. I got it about 15 millimeters from the edge, and I'm going to try to be as careful and waste as little of this material as possible. So I got one of the two small vices loosely bolted to the table. An easy way to tram a vise with this Proxxon mill is simply to pinch in a nice precision square between the table and the column. And now the vise can just be pushed up against the square, and we can now tighten these bolts down, and I'll tighten the rest of them off camera. I find this usually is able to get it trammed to within, from one side to the other, maybe 0.02 of a millimeter, or even better than that often. Now, this vise here, I situated at that location, which would be reasonable for doing a relatively large workpiece like this one I have here, but it's not ideal. If it was over here, if I moved the vise to these two slots, well, then there wouldn't be enough travel to, inward travel to cover this entire workpiece. That is going to be my hopeful improvement with this vise, other than just being a nicer vise in general. With that clamping system, I can get it exactly where I want it to be. And once again, insofar as minimizing the amount of y-axis travel outwards from the column that I need to do. Once again, you pull the table out, pull the y-axis out, table becomes a little bit wobbly. Well, for shits and giggles, let's just see how good of a tram that quick tram was. I got this zeroed and run it from one side to the other. And it's not perfectly trammed. It's now off by about 3/100ths of a millimeter. And now about 5/100ths, about 2/1000ths of an inch. Not too bad, not too great. To be honest, I do find that these vices that are screwed directly to the table, I find them a little bit difficult to get a really good tram on them, no matter how hard I try. The reason why is the bolt, the first screw that you tighten, it puts a little bit of torsion in and it throws the vise off. That's going to be one of my other hopes of this vise with separate hold down clamps, is it gives a little bit of isolation between the screw and the device itself. I hope that is going to make this a little bit easier to tram it precisely. Okay, let's talk end mills. Here are 3 end mills I have. They are all in the ESE series. You can get these on Fleabay. Indexed end mills that take carbide inserts. The one on the right takes 2 inserts. The other 2 are 3 tooth jobbies. Now, these differ insofar as what inserts I have installed. You might notice that the radius of each insert's a little bit different. On the right-hand side, it's a 0.8 millimeter radius. In the middle, it's a 0.4, and on the left-hand side is the tightest radius. That's only a 0.2 millimeter radius. Now, this mill on the right-hand side is the first end mill of this type that I had, and the first inserts I had. I used this way back with that project. I have a video on it, machining some stainless steel washers. Now, that large radius type of an insert, it has some interesting properties. For one thing, they are indestructible. The larger the radius, the less likely that they are going to chip. And after that entire project, these inserts, they look like they're practically new. However, this wide radius, it does produce much higher cutting forces. And if you check out that video on machining washers, you will find that the machine was, well, it was creating really quite the rack. It was like a machine gun. Well, I'm going to try for this project, because I'm using a free machining stainless steel. I'm going to try this end mill on the left-hand side with the tightest cutter. The tightest cutter, this is going to generate lower forces, and it should produce a nicer finish. The finish that was produced with this 2-cutter jobby and the heavily radiused edges, not the nicest surfaced finish. Anyways, let's get this installed and set it up. And we're ready to go. Here is the part mounted in the vise. It's a little bit high on that side, a little bit low on that side, difference of maybe a millimeter or so. Freehand bandsaw cut. What can you do? Except now we're going to clean it up. Speeds and feeds. Well, this isn't CNC, so it's a lot of guesstimation. Carbide insert. Carbide, I understand it likes speed, so I'm just going to use the maximum speed setting. I think it's 2500 RPM or something like that. Anyways, I got my handy-dandy Swarf Corral pieces. I'm going to install these, and they do help to some extent with reducing the amount of swarf. That one fell off. The amount of swarf that's flying around on my work table. Anyways, what I got to do first of all is touch it off. Let's turn it on. I'm going to get that zeroed. Where is the zero? There it is. And see if I can get my hand out of there. Okay, now that is just making contact metal. And with this machine, you could only take the lightest kisses of metal off. So for each pass, I'm going to do maybe 20th of a millimeter. I'll start off with that. If it works out, I'll go for a 10th of a millimeter, and maybe even a little bit more serious than that. So let's advance it here. That is a 20th of a millimeter, and do a pass. That had no problem with that. However, it was making barely any contact with the metal. Anyways, I got a bit of a milling job here in front of me. It's going to take about 5 or 10 minutes. It's going to be lots of passes and gradually lowering the tool into the metal. Anyways, I'll bring you back for the last pass. Well, not the last pass, but about 2/3 of the way through. I've ended up deciding on a vertical feed of a 10th of a millimeter for every pass, and for every pass I'm advancing it 6 millimeters, so 6 millimeter stripes. Why 6 millimeters? Well, it's 4 hand wheel jogs, four revolutions of the y-axis hand wheel, easy to remember. Anyways, this seems to balance out speed, and it's still kind of a slow operation, so let's just do one pass and show you how it works. You'll notice that that it still occasionally squeals a little bit. That's not too bad. A little bit of squealing there. Okay, 6 millimeters of advance. 2, 3, 4. Yeah, a little bit of chatter. Well, here's the end result, and honestly not the greatest result. Notice that the stripes are kind of varying in width. Also, you can see where the chatter, where it was making that squealing noise, and it wasn't cutting quite as nice there. Yeah, not the greatest finish with this ESE bit, even with the 0.2 radius carbide inserts. Here's a piece I did sometime previous. This is with the 0.8 millimeter radius, and you can see that its finish is even poorer. It's kind of like this dappled sort of a finish. Now, if you use a proper end mill, a nice and sharp end mill like one of these, it is possible to get with this mill quite a bit neater. I get the light there right. Yeah, quite a bit neater of a finish. Anyways, I'm going to try to working on that through this project with the same end mill. See if I can get it a little bit nicer. Maybe just locking down the axes and going a little bit slower might help. And the next task is to cut that block into 2 equal blocks. I scribed a line. I set it up with the slitting saw here. I could have used the bandsaw to do this, however it's really kind of a small part to hold, and not only that, the bandsaw is not very accurate. I want to save as much material as possible. This will be a while. Let's do one pass here for the camera. Not even touching. There we go. Those toe clamps I'm using are really handy problem solvers. You can tell the piece isn't put in very straight, but oh well, for this task that's not essential. Binded. This is going to be slow. So we're a little bit more than halfway through. This is really wasting a minimal amount of material. This workpiece is only barely big enough for my purposes. The slitting saw has a thickness of 1 millimeter. It's the only one I have. And the kerf that it's making is just a little bit more than a millimeter, 1.4 millimeters at the opening. Because this mill is impossible to properly tram, this blade isn't perfectly flat, and the kerf is getting a little bit more narrow as we move inwards. Anyways, for posterity, let's do one more pass. And as you can see, very slow, 1/10 of a millimeter at a time. At least now it's not binding. So here are the two parts freshly sawed. They are really close to each other. I'd say within 1/10 of a millimeter or so. It's going to require a very small amount of cleanup on the mill. Also, that slitting saw didn't make this perfectly square, so the mill will take care of that. Maybe while I'm at it, I'll do all the four sides here and get them nice and shiny. Shiny's nice. Now to do this, I want to do it at the same time, so I have both milling vices installed on the table. And to get them trammed up with each other, I stuck a parallel in here. I have the parallel clamped down. It allowed me to tram these two vices as a unit. Now, I've done this before. It's really finicky, but it is possible to get both of these vices within about 1/100 of a millimeter from one end to the other, but it's a lot of work to do that. I didn't work as hard this time, but I got it not too bad in a relatively short period of time, maybe 4 or 5 minutes of tramming. Let's just check it out here from the middle of one jaw to the end, and we're out to under 2/100ths of a millimeter. That's well under 1,000th of an inch. And on the other vise, start at 0 there, go to the middle, which is where I'll be holding the workpiece. And it's maybe 3/100ths of a millimeter, maybe a little bit less than that. Not too bad. More than adequate for this next task. I'll show you one pass here in this dual clamped setup. I'm just taking the faintest whiff of material off, 1/10 of a millimeter, just to polish off these surfaces, square them off. Let's go. Not too much chatter on this pass. Surfaces are not perfectly flat. And contact. Okay, it looks like this is going to need a second pass. Here are the two parts cleaned up on 4 sides. Now, I had to break out the computer and have it aid me in some design. And this here is the profile of these two pieces. They are 14.9 millimeters by 14.0 millimeters. And the shaded area is what I need to remove. Now, ordinarily, I would use an ordinary end mill, and I'd just side mill this inwards. That works pretty well. However, this is the only parallel I have, and it's not going to offer a lot of holding power. And side milling on it might create some forces and throw the part out. So I think I'm just going to stick with this ESE mill, and I'm going to mill, well, top down. It'll take a little while, but having the two parts set up side by side, that should help speed things up. Let me get this set up, and I'll be right back. I once again have both parts now mounted in each vise, and I'm ready to begin milling this ledge. I guess it's a rabbet. And in order to do so, I need to find the edge of the workpiece. I could do that with an edge finder tool. This here is for non-destructively finding the edge of a workpiece. But since this is going to be milled away anyways, I can do it in a much simpler manner, simply touching it off, which means pulling the workpiece into the tool bit while it's operating, and noting as soon as it makes contact, and that'll be the 0 position. Here's the hand wheel, and you can see that there's a graduated ring on that. This ring moves with the wheel, but it also can move independently, so we can hold the 0 in. And let's find where 0 is on this workpiece. Okay, so that is 0. And now we can raise the tool a bit above the workpiece. And I want to move it in 4 millimeters. I decide on 4 millimeters rather than 3.5. Each revolution is 1.5 millimeters. So 2 revolutions would be 3. That would be 1.5. That would be 3. 3.5. And that is now exactly 4 millimeters in from the edge of the workpiece. I'll bring you back for when I'm doing a couple milling passes. And we're about 1 millimeter down. A tenth of a millimeter at a time. And that's about 4 millimeters in. Well, according to the scale on the hand wheels, that should be the fine feet hand wheel. That should be 8 millimeters. However, I do know that scale leaves a little bit to be desired insofar as accuracy is concerned. So for the last little bit, I'm going to be having to check this by hand. Get in there like so. And see what that is. It's not quite 8 millimeters. It looks like it is about 7 point some odd. I can't read it through my camera, but it's not quite 8 millimeters. So the last little bit, I'm gonna just have to do really carefully and check at each pass. And that should do it. Check out how deep that is. And we have 8.3. Awesome. Now let's make another step, and this step is going to be 9 millimeters wide. So that's 1.5, 3, 4.5, 6, 7.5, and that is going to be 9 millimeters. And this next step, it's only going to be 1 millimeter deep. And here's the last of 10 shallow 10th millimeter passes. So here are the two parts in profile. They match the CAD specification pretty well. Now, these are going to clamp down on the Vise's ledge like so, and these two parts are going to make us a total of 4 clamps. Let's set up the slitting saw. Like last time, I scribed the line and I set the saw up as close to the line as I could eyeball it. I have the second part mounted in the vise just to distribute load across this mobile jaw. Let's get cutting. Bit by bit. Everything with this mill is slow. Here are the 4 parts. One of them is in the vise already. They're all within 1/10 of a millimeter of each other. I'm going to just mill it off, clean up the edge a little bit, just take a whiff of material off, make it nice and shiny. Well, here are 4 parts. 2 of them are mounted in the vise. This one here is going to be what we're working on to begin with. And I have it lined up at the edge of the jaw. And what we need to do is find the 0, the corner of this workpiece. And we need to find that because I got it on the CAD software here. Forgive me, it's Windows 95. They can put microchips in vaccines, but they're shit for graphics. Anyways, what I need to do is move in 7.5 millimeters one way and 7.5 millimeters the other way from the corner, from that side of, well, that corner of the part. Anyways, the way we're going to do this is with the edge finder, and the way this edge finder works is, well, I'll just show you how it works. I turn it on, and you can see it's wobbling like that. I'm going to put that at 0. And as I move the workpiece into the finder, you can see that the eccentricity is becoming shallower and shallower until there's almost no eccentricity anymore. Looks like it's almost perfectly centered there, but you keep going until right there. See, that's kicked out, and now that is zeroed on that side there. So I'm going to move that in. It's actually not zeroed, the edge is found. The 0 would be the center of this, which is 6 millimeters in width. So to put the spindle axis in center with that edge, I got to move this in 3 millimeters. So that's 1.5. And that is 3 millimeters. Now it's in line with that edge. Now let's move it in 7.5 millimeters. That'll put it in the center. Okay, 1.5, 3, 4.5, 6, and 7.5. I'm going to lock down this axis. There we go. Now let's find this edge. Same process. Let's get that zeroed on the hand wheel and then pull the part into the edge finder. Almost there. Okay, now it is found. Let's raise the spindle, clear the workpiece, lock it down, and once again here, that's 1.5. That is 3 millimeters. Now it's in line with the edge of the workpiece. That's now gets 7.5 inwards. That's 1.5. That's 3. That's 4.5. That's 6. And that is now 7.5 millimeters. Lock that axis down and see if it is relatively centered. Looks not too bad. I did scribe an X in them where I want the hole, and I'll check it after I load up a drill bit to get a little bit better of a pointing, but it seems like it's on the money. Anyways, let's get the drill bit loaded up. I have the mill now in drilling mode and a 6 millimeter stub bit that is put directly into a collet in the machine. I'd like it to be a little bit larger of a diameter of a bit, but 6 millimeters is nice because there's a collet that will directly fit it into the machine. It's a stub bit, so it'll be fairly accurate. And if I need to enlarge the hole, I can always enlarge it afterwards. 6 millimeters should be adequate for clearing an M6 screw. I'm going to put a drop of tapping fluid on there, and let's go. And we're through. Now let's just clean this up and rinse and repeat with the other 3 parts. Here are the drilled parts. Next thing I like to do is a counterbore for a cap screw. I have a 10mm ESE bit in here. It is a 2-fruit variety. 10mm is a little bit on the tight side for one of these cap screws, but it'll clear. It'll be adequate. Anyways, I'm going to counterbore this in 4mm. So let us turn it on. Make sure it's zeroed. It is zeroed. And this might squeal. If it does, I'll turn the volume down. Contact. Okay, 4mm. Well, that was just a 0.5mm. It's kind of noisy. I'm going to do this off of camera, and I'll bring you back when I get the counterboring done. Well, that was a near disaster. This ESE 2-fluted bit is no good whatsoever for counterboring. What happened is just like maybe a 1/3 of a millimeter further than when I stopped the video recording, it started catching, and it violently shook the machine, and it even threw it out of whack a little bit, and the hole is, the counterbore is a little bit off a center. That's a bit annoying. Anyways, I got the machine set up again, and I'm going to use a tried and true, just a standard end mill. It's roughing end mill, but for counterboring, that's not going to matter. Has a chipped corner or two, not sure. However, I used it recently in steel, and it works fine. So anyways, I'll bring you back after these counterbores are bored. The parts are all counterbored now. I got a counter stink in here. Let's add a small chamfer to the edge of this hole, maybe a 0.5mm. High-speed steel countersink, so I'm going to use it at a slow speed. And contact. 0.5mm. Ouch, that was painful. So here are the 4 parts, all milled, drilled, counterbored, and counterstunk, and they're basically ready to go. I'm just going to add a couple of finishing touches to them. This one here with the red mark is the one that got thrown, or well, nearly thrown. Oh, it did get thrown a little bit. I managed to recover, and the only problem with it is that the counterbore is just a little bit eccentric, but otherwise it's not too bad. Anyways, the first finishing touch I am going to do is I'm going to use my beveling chamfering jig. I have a video on how I made this. You can check that out. And it makes, as long as you have a belt sander, it makes adding a chamfer really easy peasy. I'm going to add a chamfer to the, the human interface edges of these little parts. Really easy to do. You just put the part in. Few random odds and ends falling off onto my bench. That should do it. Oh, check that out. What a Windows 95 user interface finish. Beauty. Now all 4 parts have the user interface edges chamfered. chamfer jig. I'm really impressed with how well that works. Anyways, I'm not super impressed with the finish that these ESE end mills leave. I was hoping for better. However, you can see where the chatter is there. It's a little bit, it's smooth, but it doesn't look wonderful. It's okay. Here on this down cut side, you can see it's quite rough there. And I'm not entirely certain that's a full 90 degrees. It looks like it's a degree or two off. So again, I'm not quite sure what that is. It's probably something to do with the spindle of this Proxxon mill not being, well, perfectly set up. Anyways, I'm quite happy nonetheless with how these parts turned out. And for the finishing touches, I am going to add these parts to my tumble vibe. I got green media in here. I kept talking about making these parts nice and shiny, shiny, shiny good, but in actuality, I kind of like the dull finish that this green pyramid media leaves. And not only does it leave a very nice matte finish that obscures a lot of the chatter that this little mill makes, it relieves the edges ever so slightly. This 416 stainless steel, it machined quite nicely in that it didn't leave much of a burr behind whatsoever. Nonetheless, these edges, they're kind of harsh. The green media, pyramid media, it relieves those edges just ever so slightly. Well, in addition to those parts, I have some T-nuts that I made some years ago. I'm going to add those to the mix, and, well, let's just cap it up and run this for, takes a while, maybe 12 hours of tumbling. Tighten that down like so, and vacate the room for about 12 hours because it's noisy. So 14 hours of tumbling, and here they are. I think that the finishes are really quite nice. I like how this tumbler, it puts a bit of a matte finish on. It doesn't completely get rid of the tool chatter and the machining marks. You can faintly see it there. Nonetheless, I do think that it makes like a really nice professional looking finish. Also, these edges, they went from being shaved with sharp to being fairly gentle, but they're still fairly hard edges. Like, it doesn't really wear them down much. The corners are a little bit worn down, so I wouldn't want to be putting these parts in for more than 12, 14 hours, something like that. Anyways, I'm quite happy with these. This here is 416 stainless steel. Now, I had tumbled some 316 stainless steel parts that I machined some time before, and 316 on the Proxxon mill machines just fine. This here one was milled with a conventional end mill, one of these carbide types, and it does a pretty decent finish. Yeah, I don't mind 316. However, it does tend to be more gummy. That's what machinists call it. It tends to get a lot more of a burr. I did find that this 416 stainless steel, it left hardly any burr behind. That was kind of pleasant. Also, 416 stainless steel, free machining, what that would refer to is, well, it's easy on tool life. But let's take a look here at the ESE end mill that removed a lot of stainless steel, and you can see all of the inserts are just in perfect condition. A little bit of the coating is worn off, but there's no chips or anything like that. I don't think that this left as nice of a finish as conventional end mill. However, for roughing out, I think it's a great option. These last forever. Now, I unmisfortunately identified a problem while testing these clamps out. The problem is, as the screw is tightened down, well, it's twisting the clamp. That's a bit annoying. I think that the problem has to do with the bottom of the counterbore being kind of rough. This is, well, it's scratchy. I'm not sure whether the microphone is picking that up or not. Yeah, it's a little bit scratchy. The bottom of the counterbore is a bit on the rough side. So I really need to use these with a washer. I don't think there's a washer that'll fit in there, though, so I got to figure out some way to make these screws seat a little bit more smoothly. Now here's how I could best figure out how to flatten out and smooth out the bottom of the counterbores. I got a diamond bit in here that just happens to be just perfectly sized to fit in this counterbore. And I'll give it just a little shot of machine oil. And I'll just do it by hand really gently. Yeah, hopefully that worked. So it's much less scratchy now than it was before. Let's see whether it moves on the vise or not when I tighten it down. It might have moved a little bit, but not too bad. Awesome. Now, one of the hopes that I have with this vise and these clamps is that it will be a little bit easier to do a quick tram of this vise. Let's say I want to have the vise 8 millimeters from the end of the table. Got a big parallel pinched in here, and this is an 8 millimeter spacer. And providing this doesn't get torsioned too much, it should be fairly well trammed. And you just tighten down these clamps, one by each. Okay, that one and that one. Now let's pull those out, roll the table down, and get this indicator into position. And that's a 0. Yeah, that's pretty good. I'm going to lock the table down. And let's see how it is across the width of the jaw. Not too bad. Not too bad. Looks like for maybe 1/100th of a millimeter out from end to end. This is a 60 millimeter wide vise, so that's not too bad. If I really wanted to get it super accurate, it'd be possible to tap this vise with a hammer and get it into position. Anyways, thanks for watching. Hope you found this useful. Subscribe, and I'll see you next time. Bye-bye.